Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are looking at Chapter 6, Thermodynamic Models of Real and Pure Compounds, and we are going to continue our development of new equations that can be used to solve practical problems based on this very fancy math. So as a reminder, we have our fundamental property relations that also tell us the natural variables of these various functions. So U is a natural function of S and V because it is defined in its fundamental relation as TdS minus PdV. dH is TdS plus VdP, making it a natural function of S and P. In this lesson, we're going to be looking at how we can apply these rules so that instead of S and P, where S is a little unfortunate, we could perhaps recast this to be in terms of variables that would be easier to work with. Our other tool that we have is the Maxwell relations. These are the second-order mixed partial derivatives of the various fundamental relations. So could we use the skills that we have at this point to develop a formula for H as a function of temperature and pressure? Much better than entropy and pressure. To do this, we want to start by taking the total differential of H in terms of temperature and pressure. Let's just basically declare it as a function of T and P. What would that look like? So dH is the derivative of H with respect to T at constant pressure dt, plus the derivative of H with respect to P at constant temperature dP. By definition, we've already seen since early in the course that C sub P is dH dt at constant pressure. So therefore, we've already got one simplification. But what about the dH dP at constant temperature? For this, we'll go to the fundamental relations. For the dH equals TdS plus VdP, we want to, instead of the differential form, recast it in the derivative form with respect to T at constant P. In this case, it gives us dH dP at constant temperature equals T ds dP at constant temperature plus V times dP dP at constant temperature, but that's just one. Now, I'm fine with having V and T in this expression, but the ds dP at constant temperature, oh, that's a problem. I don't know all that much about entropy, and much less how does it change with pressure? I don't know. So this is where we use a Maxwell. Since ds dP at constant T is negative dV dt at constant P, we end up with dH dP at constant T equals V minus T dV dt at constant pressure. And if we substitute this back into our initial differential form, we see that dH is Cp dt plus V minus T times dV dt at constant pressure, quantity times dP. So we now have H as a function of temperature and pressure, all in terms of things that we can measure or look up. Now we can evaluate this as long as we have a relationship for how V changes with T at constant pressure. Let's look at this for an ideal gas and see if it matches what we found earlier. I find that this is a very useful way to check any of my math that I do in these processes. There are so many places that you could have gone wrong, right? But I know what the answer should be for an ideal gas as a function of temperature and pressure, right? It shouldn't change with pressure. It should just be Cp dt. And so therefore, let's do this applying the ideal gas law, RT equals PV, or V is equal to RT over P. Now, of course, these are per unit mole or per unit mass, but I can take that derivative. dV dt at constant P for the ideal gas law, well, I'm holding P constant, so R and P are constant. Therefore, it's just those two constants, R over P. And now I can substitute this in to my expression for dH. dH for the ideal gas, so I used a superscript Ig to indicate that, is C sub P naught. Remember, C sub P with the superscript 0 on it indicates the ideal gas value for C sub P, and that means it's something that we could, in fact, look up, plus V minus T times R over P. But RT over P, that's just V. So I really have dH for the ideal gas is C sub P naught dt plus V minus V dP, or the expected result, dH for our ideal gas is C sub P naught dt. What about if the gas obeyed a different equation of state, one that was a little more complicated? So let's look at the van der Waals equation of state. P equals RT over V minus B minus A over V squared, where B and A are defined for whatever our gas is, our substance is. I need to find dV dt at constant pressure. But I can't solve explicitly for V in this expression. And although I can do implicit differentiation, oh, yuck, that's gonna be hard. Is there perhaps something else that we could do? In this case, my equation of state is written as P is a function of temperature and volume. So it would be much easier if I had an expression for H as a function of temperature and volume. So let's go through the steps that we just did to find H as a function of temperature and pressure. First, we'll write it as differential form, where T and V are my variables, dH dt at constant V dt plus dH dV at constant T dV. dH dt at constant V is the definition of C sub V. For dH dV at constant T, I'll use the fundamental relation. Therefore, dH is CV dt plus the quantity T ds dV at constant T plus V dP dV at constant T, all times dV. I can use a Maxwell to get rid of the S. Hopefully you're starting to see a pattern here that we do very similar steps each time. So the Maxwell in this case, ds dV at constant T, is equal to dP dt at constant V. I can take these derivatives for our equation of state. In the case of dP dt at constant volume, A over V squared is a constant, so therefore dP dt at constant volume is simply R over V minus B. dP dV at constant volume, holding T constant, is somewhat more challenging, but this is really just V raised to a negative power, so RT over V minus B squared plus 2A over V cubed. I can substitute the, and I end up with dH is C sub V dt plus RT over V minus B plus negative RTV over V minus B squared plus 2A over V squared dV. I can play a little algebra trick here. I have two terms of V minus B in the denominator, 1 to the first power 1 squared. If I multiply top and bottom by v minus b, I end up with v minus b squared in both of those, and therefore I can combine them and get a ever so slightly simpler equation. dH is c sub v dt plus the quantity 2a over v squared minus brt over v minus b squared, all times dv. If I knew the values of a, b, and I had a change in temperature and a change in volume, this could be integrated to find dH. In our next video lesson, we're going to introduce some new measurable quantities and look at ways that we might use those. This concludes this video. Thank you very much for your time.